Hello, good morning to everyone. This is Kumar K from National Engineering College, Koval. So, good morning, everyone. In today's class, we are going to see about the topic parity checker as well as generator. In the field of digital electronics, it is of very important to ensure the data integrity. So, in order to make the data integrity, and we need the two purpose. One is we have parity generator, and the second thing we have parity checker. So both these parity generator as well as checker, they help to detect and correct any kind of error during the data transmission. So what does mean by parity bit? In case of your digital signal processing, if we add some extra bit, that bit can be 0 or 1. So this extra bit is added along with the original binary or digital code in order to detect and correct any kind of error that has been happened during the transmission of the original data. So this additional bit is called as parity bit, and the bit that can be generated by the circuit is called as parity check generator, and the circuit which checks the error is called as parity checker. So the addition of parity bit to the original data makes the total number of ones either in odd numbers or in even numbers. Suppose if the number of ones in the data, it can be classified into two types, that can be even parity or odd parity. So what does mean by even parity? If the total number of ones along with the parity bit, what to say, let us take the example of a 3-bit binary information ABC. That ABC information has to be sended along with the parity bit P. That's why now your present bit is 4-bit. Among the 4-bit, your 3-bit is your original bit and your 4th bit is your parity bit, isn't it? So if the 4-bit constitutes the even number of ones, then it becomes the even parity, or else if it contains odd number of ones, then it becomes your odd parity. So here in case of your even parity generator, let us take the 3-bit message. That message be for bits ABC, and in order to transmit the 3-bit information, we need some extra bit, that is parity bit P, to ensure that the sender information is correctly sent and the receiver get the correct information. To ensure that, we are in need of this parity bit. Okay, so next is odd parity generator. In case of even parity generator, your we will be having even number of ones, isn't it? So in case of odd parity generator, the bit along with the original information, you should contain odd number of ones. That is the difference between your even parity as well as your odd parity. So what is your parity checker? The parity checker will check the possibility of error. Suppose if we are sending the information and we have used the even parity bit along with the original information, then the even parity checker will check at the receiving end whether the sending end have sent the even number of ones, that is the information contain even number of ones. If there is no even number of ones, then it is said to be an error. That's why your parity checker will indicate the error as 1, that is it is denoted by a bit 1. If it is no error, then it is indicated by a bit 0. This can be seen here. See, in case of your even parity checker, let us consider the 3 input message, that is A, B, C. So this 3 input message, what is the possibility of this inputs? From 000 to 111, isn't it? 000, 001, 010, like that. It will be having 8 inputs ranging from 0 to 7. Okay. In addition to that original information, we are adding some extra bit, that is nothing but parity bit. So let us see here. This case is even parity checker. So these two rows become same inputs. See, A is equal to 0, B is equal to 0, C is equal to 0. Again, A is equal to 0, B is equal to 0, C is equal to 0. So these two rows constitute case 1. In this case 1, for first row, we are adding the parity bit as 0. See here, we can't able to see even a single number of ones, and all the bits are 0. So there is no error. But if you see the second row, you will be getting odd number of ones, but we are using even parity generator, so this becomes the error, isn't it? Actually what we should get even number of ones, but here you are getting odd number of ones. That's why it is error. That error is indicated by your parity even parity checker, which is indicated by your bit 1. See the second case, your bit is 0 0 1 0 0 1. If you are adding parity bit 0, see here the third row, you will be getting odd number of ones, that's why it is an error. See the fourth row, it is even number of ones, then there is no error, that's why it is indicated by a bit 0. Similarly, likewise, you will be continuing with the n number of inputs. See the last case here, that is 111. If you are adding 0, then the whole see the row here, it will be having odd number of ones, that is it results in an error. And see the last row, you are having even number of ones, so there is no error, which is indicated by 0 by the even parity bit. If you are plotting this truth table in 4 variable K-map, so these 4 are the inputs, AB and CP are the inputs, and you plot this output in a 4 variable K-map, you will be getting the expression as A XOR B XOR C XOR D. Likewise, for odd parity checker, what you will identify, you have to get odd number of ones. If you generate odd number of ones, then it becomes error free. In other words, if you are generating even number of ones in addition to the parity bit, see here the fourth row, you will be getting even number of ones, isn't it? Then the odd parity checker will check and it indicate that no, wrong, it was an error, so that error will be indicated by your number 1. Similarly, you have to do for all the cases. And if you are plotting using the 4 variable K-map, you will be getting the expression as A XOR B XOR C XOR D.